Thank you for that introduction, Nikolai. As mentioned, my name is Malte Suppli, and I'm a PhD student at Gentofte Hospital in Philip Knop's group. And I have the honor of introducing this concept to you, or discussing this concept with you, together with Sara and Marie. The background, I'm going to give you a bit of a warning. You've seen it before, but so the opinion of my 2-year-old daughter is you can never hear a good story too many times, so I hope you feel somewhat the same way. This graph is, this figure is by a study performed by Jonathan Bakker from our group, and it's just to show you that patients with type 2 diabetes, illustrated by the red graph, have fasting hyperglucagonemia, and as Philip also showed you yesterday, this actually contributes to the hyperglycemia of these patients. So it is a relevant clinical problem to address and trying to figure out why do these patients with type 2 diabetes in fact have hyperglucagonemia. This is a study performed by Philip, you saw it yesterday as well. Lean and obese patients with type 2 diabetes in the top, and obese and healthy lean healthy individuals in the bottom. And what was perhaps somewhat surprising is that the common denominator in terms of fasting hyperglucagonemia was obesity rather than the diabetic state. So perhaps this problem with fasting hyperglucagonemia is actually a consequence of obesity rather than something that's a consequence of type 2 diabetes. You've also seen this figure before. I guess you can't really leave this conference without knowing this figure. These were analyses performed by Nikolaj Albrechtsen on a study performed by Anders Juncker, and I couldn't really find a picture of him, so I left it out. But it's patients with type 2 diabetes with and without non-alcoholic fatty liver disease, patients with only non-alcoholic fatty liver disease and healthy controls, and as you've seen before, fasting hyperglucagonemia in the groups with non-alcoholic fatty liver disease. So perhaps we can zoom in even further than obesity, and actually maybe fasting hyperglucagonemia is a consequence of non-alcoholic fatty liver disease. We could put a question mark to this after what Nikolai showed us this morning, so perhaps it's both obesity and non-alcoholic fatty liver disease. And you've also seen this before, fasting hyperaminoacidemia in the two groups with non-alcoholic fatty liver disease. And these results and numerous others, among others performed by Daniel Dinu, whom you heard yesterday, led to the development of this hypothesis about the liver alpha cell axis, which Nikolai just touched upon. So we know that glucagon stimulates lipolysis, urea synthesis, or the turnover of amino acids in the liver, and also glucose production in the liver. And we know that amino acids stimulate the secretion of glucagon from the pancreatic alpha cells. So the concept that was pioneered by Jens, Nikolai, and Philip, and various other researchers is that when you develop non-alcoholic fatty liver disease, the liver becomes resistant to glucagon, at least at the level of amino acid turnover, leading to a reduction in the turnover of amino acids. This leads to increased circulating amino acids in plasma, which stimulate the secretion of glucagon from pancreatic alpha cells. And there you have it, perhaps the explanation for fasting hyperglucagonemia in patients with non-alcoholic fatty liver disease. So this is the concept we will try to explore further during the session. And I will turn the microphone over to Marie.
Thank you. So I'll show you some data from our group where we work with glucagon's effects on amino acid metabolism and glucagon resistance in rodents. So the first data is from a study performed by my colleagues Katrine and Emilie. They treated mice with either a glucagon analog or a glucagon receptor antibody for 4 weeks. The mice that received the long-term, long-acting glucagon agonist showed hyperaminoacidemia after 4 weeks, and this was evident at the level of each of the individual amino acids. Oppositely, in the mice that received the glucagon receptor antibody, these mice showed hyperaminoacidemia, again at the level of each individual amino acids, really emphasizing how important glucagon is for amino acid catabolism. Mm-hmm. Okay, sorry. In a bit more acute setting, we treated mice with a glucagon receptor antagonist for 3 hours. And after 3 hours, these mice had elevated levels of glucagon and amino acids. demonstrating disruption of the liver alpha cell axis. The mice were subjected to an amino acid challenge, and we measured plasma levels of urea as a marker for amino acid catabolism. And as you can see, the mice treated with the glucagon receptor antagonist produced less urea in response to amino acids compared to the control mice. So next we looked into the effects of hepatic steatosis on the liver alpha cell axis. As a model, we used the OB mice. And these mice also have elevated levels of glucagon as well as amino acids, demonstrating disruption of the liver alpha cell axis. These mice were also subjected to an amino acid challenge, and the OB mice produced less urea than the control mice in response to amino acids. And this was confirmed in vitro, and primary hepatocytes from the OB mice produced less urea in response to amino acids compared to the control. So the results from the in vivo studies from the OB mice looked very similar to the results from the mice treated with the glucagon receptor antagonist, suggesting that there is a link between hepatic steatosis and reduced glucagon signaling. To directly test if hepatic steatosis leads to glucagon resistance, we used the perfused rat liver experiment where we have so we use sugar fatty rats as a model for hepatic steatosis and control rats as controls. The livers were perfused through the portal vein, and we collect the outflow from the upper vena cava inferior. In the lean rats, as expected, there's a production of urea when we infuse with a mixture of amino acids. And glucagon alone does not alter urea production, but when we gave glucagon together with the amino acids, we saw a synergistic effect and significantly increased urea production. In the fatty rats with hepatic steatosis, we got similar urea production in response to amino acids, but importantly, there was no additional effect of glucagon, suggesting that these mice are glucagon resistant. What could be the mechanism for this glucagon resistance? We performed RNA sequencing on livers from glucagon receptor knockout mice as a model for extreme glucagon resistance, and also on mice that were fed a high-fat diet and fructose water, which induced a mild version of hepatic steatosis. The glucagon receptor knockout mice have many genes involved in urea cycle and amino acid transport that are downregulated. And 3 of these genes overlap from the RNA sequencing from the mice with hepatic steatosis. One of them is the arginine transporter SLC7A2 we heard about yesterday in Daniel Dean's talk, but also CPS1, which is the first and rate-limiting enzyme of the urea cycle. So we hypothesized that some of these genes are involved in the mechanisms behind the glucagon resistance we observe in hepatic steatosis. We also measured the activity of CPS1 enzyme, which was reduced in glucagon receptor knockout mice, as well as in the OB mice with hepatic steatosis. And in another experiment, we also saw an increase in the activity of CPS1 2 hours after treatment with a glucagon analog. So in addition to the transcriptional regulation, there may also be non-transcriptional mechanisms contributing to the glucagon resistance in hepatic steatosis. So to summarize, hepatic steatosis may disrupt the liver alpha cell axis due to impaired hepatic actions of glucagon, which results in reduced ureagenesis and increased levels of plasma amino acids, stimulating to this hypersecretion of glucagon. So the question is, does the data we observe in mice and rats translate to humans?
And I will try to elaborate a bit on that. A main challenge when we want to evaluate the effects of glucagon is that insulin is a very, very powerful hormone, and it counter-regulates a lot of the effects of glucagon. So a nice way to study the isolated effects of glucagon is to apply a pancreatic clamp. Jens talked briefly about this yesterday, but I'm just going to take you through the method quickly. For my studies, we first infused stable isotope-marked glucose tracers to assess the endogenous glucose production, and then at time 0, we initiated an infusion of somatostatin, which completely inhibits the secretion of endocrine hormones from the pancreas. This allows us to substitute insulin at a basal level, and together with that, glucagon at a basal level. But we're also able to increase the infusion rate of glucagon markedly while maintaining a stable infusion rate of insulin, so we can assess the effects of glucagon without any counterregulation by insulin. This is Koch et al. In 1974 who described this pancreatic clamp as the actions of somatostatin simulate those of an acute reversible endocrine pancreatectomy. So I really like that quote, sums it up nicely. So for my first study, we included 15 obese individuals and 15 lean individuals, and the thought was that the obese group would have a high degree of hepatic steatosis. We evaluated that by taking a liver biopsy, and they did in fact have 14 out of 15 had hepatic steatosis, but to a very varying degree. And these are the C-peptide concentrations during the pancreatic clamp, just to show you that when at time 0 we initiate the somatostatin infusion, C-peptide concentrations drop immediately, showing really nicely that we have in fact inhibited the endocrine pancreas. Insulin concentrations were kept stable throughout the pancreatic clamp, again as we wanted them to be, and when we increased the infusion rate of glucagon, naturally the concentrations of glucagon increased, but I hope this convinces you that we are actually able to assess effects of high glucagon levels without any changes in insulin. So let's look at glucose production. We have talked mostly about amino acids during this conference, but of course we know that glucagon has a very powerful stimulatory effect on glucose. But so these are the this is the endogenous glucose production in the two groups. You can see when we increase the infusion rate of glucagon, the endogenous glucose production increases exactly as we would expect. But when we look at the incremental area under the curve, that is the increase in endogenous glucose production, there was no difference between the groups. So really no signs of glucagon resistance with regards to glucose production. And actually, at first, a couple of years back when I found this, I was a bit disappointed. I was hoping to find glucagon resistance, but it actually it nicely explains why we can even discuss the concept of hepatic glucagon resistance while also thinking about how this glucagon can increase glucose levels in the patient with type 2 diabetes. So actually it fits nicely with the model. But I guess amino acid concentrations are the most interesting in this setting. First, if you look at the fasting concentration of amino acids, you can see that the obese group had elevated concentrations compared to the lean. So this corresponds really nicely to what you've seen earlier. During the basal infusion of glucagon, we didn't really see any changes in amino acid concentrations as we would expect. But when we increased the infusion rate of glucagon, something really interesting happened. First, if you look at the lean group, amino acid concentrations decreased as you would expect. We know that glucagon stimulates the turnover of amino acids. But in the obese group, we actually saw a slight increase in amino acid concentrations, which is completely paradoxical as to what we know of the effects of glucagon on the liver. So we interpreted this as a sign of hepatic glucagon resistance in this obese group with a high prevalence of non-alcoholic fatty liver disease. So we have performed liver biopsies, and we also looked at the regulation of pathways in the two groups. This is the pathways in the obese group compared to the lean. And as you can see on the left, more pathways were downregulated in the obese group compared to the lean. But more importantly, we found that the most downregulated pathways were involved in the metabolism of amino acids and derivatives, and also SLC-mediated transmembrane transport. So that's, again, really nicely correlates with what you've seen earlier. We also looked at the specific transcription of genes and found a downregulation of several amino acid transporters. I'll point to SLC7A2 again, as shown by Daniel Dean and Marie just earlier, and also CPS1, which was downregulated as in the rodent studies Marie just showed you. So, so far it fits really nicely. So we also wanted to see, so this is, there are numerous differences between obese and lean individuals, and we also wanted to see, can this effect in fact be induced acutely in lean individuals? So we included 20 healthy male individuals who had a normal lifestyle, didn't do too much exercise, ate according to the Nordic nutrition recommendations. And we subjected them to a hypercaloric diet of approximately 5,000 kilocalories per day for 2 weeks. Asked them to live a sedentary lifestyle, no exercise, maximum of 5,000 steps per day. And then after 8 weeks, at week 10, we asked them to come to a follow-up visit, and we did a pancreatic clamp on all 3 occasions. Just to show you what happens when you eat 5,000 calories per day for 2 weeks, they increased their weight significantly, and they were in fact not able to reduce the weight in 2 months afterwards. Waist circumference increased by around 5 centimeters and was reduced to normal, and their fat mass increased by around 1.8%. Liver enzymes increased significantly and were back to normal after 8 weeks. And liver fat assessed by MR spectroscopy also increased after the 2 weeks. I should say that the statistics performed on these, you can see that they're not normally distributed, but we did log transformation before the statistics. I just wanted to show you the raw data. So, just to show you the pancreatic clamp once again, this is exactly as before. A nice inhibition of the endocrine pancreas, stable insulin levels, perhaps a slight increase towards the end in all 3 days, but not significantly different between the groups, and increases in glucagon as we would want. So, amino acids. At baseline, we saw a decrease in amino acid concentrations during the high infusion rate of glucagon, exactly as we would expect. But after the hypercaloric diet intervention, we actually saw a shift in the graph, and it went the right way. So perhaps indicating some glucagon resistance. There's a lot of variation in the data, so perhaps you're not so convinced yet. But what I hope will convince you is that when we invited them back for the follow-up visit, the amino acid graph went completely back to what we saw before the intervention. So again, this is an acute setting, only 2 weeks of a hypercaloric diet intervention, but actually, to me, this indicates that some sort of glucagon resistance also in the acute state. We looked at the average slope of the graphs to kind of illustrate the turnover rate of amino acids, kind of a proxy for that, and that was reduced after the hypercaloric diet. And we also had pre-specified, perhaps luckily, that we wanted to look at the percentage change in amino acids during the last hour of the pancreatic clamp, and saw almost no change in the after the hypercaloric diet, as opposed to the baseline and follow-up visits. So again, indicating glucagon resistance in these patients, these healthy individuals after only 2 weeks. So, lastly, I'm going to show you these results by Sofie Hedersdal. She evaluated amino acid and glucagon concentrations in 2 groups, patients with type 2 diabetes and healthy controls. And so we discussed that perhaps non-alcoholic fatty liver disease kind of is this model of induces glucagon resistance. But Sofie did an almost perfect model of glucagon resistance. She applied a glucagon receptor antagonist, completely abolishing the effects of glucagon. And what happened? As we would expect, amino acid concentrations increased together with glucagon concentration, again supporting this concept of the liver alpha cell axis when we have hepatic glucagon resistance. So that was it from me. I'm going to turn the microphone over to Sara.
Yeah. Hello. Yeah, I think we're going to shift back and forth, so no worries about the clapping. It's going to be too much in the end, I think. I'm here to take the concept of glucagon resistance to the next level, to the lipids. And you have to forgive me for my change in terminology. For this paper, we decided to go modern and call non-alcoholic fatty liver disease, NAFLD, for MAFL, for metabolic dysfunction-associated fatty liver disease. See, realizing there's hepatologists here that might disagree, I would argue that the biggest problem for the patient with a fatty liver, at least the one most likely to cause death, is the increased risk of diabetes and atherosclerosis perhaps resulting in cardiovascular disease. That was our starting point. So to some extent, atherogenic LDL is derived from a hepatic VLDL-triglyceride. So what actually determines the rate of hepatic VLDL-triglyceride secretion in humans? Ignoring all details, the supply of free fatty acids to the liver from adipose tissue lipolysis and from dairy sources stimulates secretion. Insulin suppresses, directly governing de novo lipogenesis and through suppression of adipose tissue lipolysis. And glucagon suppresses, probably reserving the lipids as fuel for the liver while it's busy making glucose for the rest of the body. Of course, all of this can go wrong in the fatty liver. Adipose tissue overflow, dysfunction, and insulin resistance causes an increased flux of fatty acids to the liver. Also, NAFLD, along with increased de novo lipogenesis and hepatic lipid insulin resistance, causes an increased VLDL secretion from the NAFLD patient. A reasonable way for the liver to get rid of some of the extra lipid to begin with, but resulting in dyslipidemia and cardiovascular trouble in the long run. So this is where we zoom in on our common interest, glucagon. Does glucagon reduce VLDL triglyceride secretion in patients with fatty liver to the same extent as in healthy overweight control subjects? Or perhaps we see an inadequate response to glucagon on hepatic lipid metabolism as we do in amino acids. For this study, we recruited 28 subjects with obesity. Based on the results of the MR spectroscopy, we divided them into controls and NAFLD subjects. Based on the liver biopsy, we identified patients with simple steatosis. We call it NAFLD minus here, the light blue color, or NAFLD, or with steatohepatitis, we call it NAFLD plus here. Though matched on age, sex, and weight, body weight, NAFLD and especially NAFLD plus, the steatohepatitis subjects, were more insulin resistant, had a higher level of visceral fat than controls. Finally, participants came for a long study day where they were submitted to a somatostatin, a pancreatic clamp. We used more or less the same setup as Malte just explained. So to pause hormone production, we used the somatostatin analog octreotide. We gave replacement doses of insulin and growth hormone, insulin in a somewhat higher dose than Malte because we used an all-obese cohort. We infused low-dose glucagon for the first 4.5 hours and then glucagon at a somewhat higher rate for the next 3 hours. We used tracer techniques to test VLDL turnover, endogenous glucose production, and peripheral lipolysis. And I promised my supervisor to tell you that this VLDL triglyceride, tracer is an in-house technique where we take out and isolate the patient's own VLDL triglyceride, label it with triolene, and give it back on the study day. This was a great relief to make up this graph showing that glucagon concentrations made sense and were alike in all groups. We used Makodi also. As you can see by the sampling C-peptide levels, octreotide is quite effective in stopping endogenous insulin production in all groups. How about insulin? Well, insulin levels were stable between low glucagon and high glucagon. At baseline, subjects with NAFLD were higher in insulin, and they stayed higher, although infusion doses were the same. This is expected, seeing that NAFLD patients have a lower insulin clearance due to them being insulin resistant. We do have to bear it in mind when interpreting our data, seeing that insulin, as well as glucagon, lowers VLDL triglyceride secretion. So, VLDL secretion rate was reduced by high glucagon in all groups. However, we do find a significant difference between groups, as you can see here by the repeated measurement ANOVA interaction. This is better illustrated on this graph, showing the percentage reduction in VLDL-triglyceride secretion. We find a 36% reduction in the control group, whereas only an 11% reduction in the NAFLD groups. The difference in glucagon effect on VLDL secretion was reflected in plasma concentrations, where we saw a slight reduction among controls and stable values among NAFLD patients. Data on total triglyceride levels reflect the same. We found no difference in the glucagon-mediated effect on endogenous glucose production, at least not at these a bit higher insulin concentrations. After increasing the glucagon infusion rate, we saw a slight increase in endogenous glucose production, and it was similar in the three groups, and the effect is wearing out pretty quickly. Data on plasma glucose reflect the same. So, NAFLD plus patient had a higher palmitate flux compared with controls generally. However, palmitate flux did not change differently between groups, and it remained stable between low glucagon and high glucagon. So this very crude measure does not support an activation of peripheral lipolysis in high glucagon states. So from this, we can conclude that subjects with NAFLD, simple steatosis, as well as steatohepatitis, have a reduced glucagon-mediated suppression of VLDL-triglyceride secretion, despite similar effect on endogenous glucose production, and despite higher insulin levels in the NAFLD groups, insulin also lowering VLDL-triglyceride secretion. So a reduced glucagon sensitivity may add to the dyslipidemia that we see in patients with NAFLD. Perhaps it's not that big of a deal to the patients because they have elevated glucagon levels, which will probably compensate for most patients. When interpreting our data, I'm not too comfortable talking about glucagon resistance as such. There may be many and other explanations for what we are finding for the reduced efficacy of glucagon on lipid metabolism. I'm not one to tell you about mechanisms, and my study certainly doesn't offer any mechanistic results. Just speculating, perhaps it's a matter of downregulation of hepatic glucagon receptors. Perhaps it's due to the different pathway perturbations of fatty liver disease, MPK disruption, or SCRIP1C activation. Or perhaps it's more a question of substrate availability, so that hepatic and peripheral insulin resistance and hepatic steatosis in itself drive the supply of fatty acids up. So we find a reduced glucagon sensitivity in hepatic lipid metabolism, specifically on VLDL triglyceride secretion in patients with NAFLD, but we don't know why this happens yet. And a bit on measurements. Yeah.
So the last topic of our talk here is about how can we measure glucagon sensitivity. And now we're back to glucagon resistant towards amino acid catabolism. So one option would be to have a biomarker for glucagon resistance. And we've seen this before, but it's always good to reproduce the data. So this is by Josefine and Liselotte from Hvidovre Hospital, who found the elevated plasma levels of glucagon as well as total amino acids in patients with biopsy-verified NAFLD, independently of whether they have type 2 diabetes or not. So here they measured total amino acid levels, but what we have seen in other human and also animal studies is that particularly alanine seems to be important for the liver alpha cell axis. And therefore, the glucagon-alanine index has been proposed as a biomarker for glucagon resistance. And to calculate this, it's just the product of fasting levels of glucagon and fasting levels of alanine. And as you can see here, the glucagon-alanine index increases in patients with hepatic steatosis and NASH. And it has been reproduced in several other studies that liver fat increases the glucagon-alanine index. We also calculated the glucagon-alanine index in a weight loss study where obese individuals lost weight with a very low-calorie diet and then entered a one-year weight maintenance program. And you can see that the glucagon-alanine index decreases with the weight loss and remains low in the weight maintenance periods, indicating that a reduction in liver fat can normalize the glucagon-alanine index. The second option would be to have an experimental test in humans. And my colleagues Sasha, Michael, Jørgen, and Nikolai are currently working on developing and testing this in humans. The test consists of 2 experimental days. On the first day, the participants, after an overnight fast, receive a bolus of glucagon IV. And on the second experimental day, they receive an amino acid infusion. For this study, they have recruited lean individuals and individuals with overweight or obesity. And they used MRI and bioimpedance analysis to assess liver fat and whole body composition. So on the first day, where they receive a bolus of glucagon, we see that plasma levels of amino acid decrease more in the lean controls compared to the overweight and obese individuals. And it's important here to mention that this is very preliminary data. This is only from 3 individuals per group. But it indicates that the obese and overweight individuals may be glucagon resistant towards the amino acid catabolism. Similar to what you've seen before, it doesn't look like they are resistant to the effects of glucagon on glucose production, here reflected by the blood glucose levels. For the second experimental day, where they receive an infusion with amino acids, we propose a glucagon sensitivity index. This is inspired by the Matsuda index for hepatic or for insulin resistance, and it uses fasting levels of amino acids and glucagon, as well as the plasma levels of amino acids and glucagon during the amino acid infusion. And even though this is very preliminary with only 3 individuals per group, we already see a very nice separation of the controls and the individuals with hepatic steatosis in this glucagon sensitivity index. So it's going to be very exciting to finish this study, and hopefully we will then have a test to measure glucagon sensitivity. Right. So what do we know about glucagon resistance? Today we have shown you that rats with hepatic steatosis are resistant to the stimulatory effects of glucagon on amino acid catabolism.
Yeah, and you've seen that obese individuals with high hepatic steatosis are glucagon resistant, and also that glucagon resistance seems to be able to be induced in only 2 weeks of a hypercaloric diet to completely healthy lean individuals. And you've also seen that endogenous glucose production is maintained, even despite hepatic steatosis, perhaps explaining why we can see elevated glucose as a consequence of hyperglucagonemia in obese individuals with hepatic steatosis.
We find that NAFLD patients have a reduced glucagon-mediated suppression of VLDL-triglyceride secretion.
And we've also shown you that a model of complete glucagon resistance induced by a glucagon receptor antagonist also supports the concept of the liver alpha cell axis.
And finally, we are currently developing a test to measure glucagon sensitivity in humans.
So that's it.
So thank you very much for this beautiful overview, and I think we've got questions already for you. Can I ask them?
Thanks a lot. That was great. Wonderful talks. So one question about for Malte about I assume they come in fasting, so there's no contribution from glycogen. That was one question. And then you looked at the enzymes involved in ureagenesis and saw that they were decreased in the NAFLD. What about PepsiK and glucose-6-phosphatase?
To be honest, I don't remember, but I think we would have included them if they were downregulated. But I'll have to go back in the data.
Because that was showing the resistance right between the two systems.
Yeah, but I'll have to go back and look in the data.
Thank you very much. That's really fantastic work. With regard to liver alpha cell axis, you saw there was a graph there where you gave the glucagon analog, the long-acting analog, and there was a broad reduction in the amino acids. And it seems to be that all of the amino acids are affected to some degree, but obviously the alanine is maybe more severely affected. Things like lysine that you don't really think about first are also quite affected. Do you have any ideas or thoughts about what those kind of amino acids may be doing within this sort of physiological axis?
We've measured all the individual amino acids for the diet intervention study, and it's been touched briefly upon. It's really difficult when you work with amino acids because they go into different fluxes and they transaminate, and it's way more complicated, at least in my opinion, than measuring glucose. So a lot of the individual amino acids, we kind of see small changes, but nothing really significant. So it kind of seems like it adds up. A lot of small changes in all the amino acids that adds up. But we didn't see any significant changes in either alanine or lysine glycine.
So I can just add a bit. So Katrine, who is here today, performed a study, and you've seen some of the results yesterday, where they gave each individual amino acids to the perfused mouse pancreas, and saw that, I can't remember all of them, but alanine was, of course, one of the most stimulatory amino acids. And in the same study, they also tested the effect of glucagon on clearance on these amino acids in vivo, and found that it was more or less the same amino acids that were regulated, the clearance of which were regulated by glucagon in vivo. So it seems that some of the amino acids are involved in the liver alpha cell axis, and some of them are actually not.
I might also add, I haven't opened the black box yet, but I do have amino acid results also. So I'm hoping maybe to be able to entangle whether what's hepatic fatty liver, what's obesity, and try and make us smarter on that.
So, Sarah, can I ask a question, Sarah? So regarding your study, did you include a measurement of beta-hydroxybutyrate to understand if the VLDL, instead of getting excreted from the liver, goes into oxidation? That was one question.
Yeah.
And then I wonder, with all this, how glucagon will work in patients with PLA3 mutations, because that's, of course, 40% of NASH patients.
For your first question, I just received the data not very long ago. I did a lot of shifts since then. I haven't been really looking at it, but I do remember thinking I'm going to be disappointed here. But it's not necessarily, it's hard to detangle whether. I think I may not find anything there, no differences. I don't know yet because I didn't quite look. Exactly. And I would have loved to be able to maybe, test the beta oxidation in a better way. I think there might be traceaways, PET, CT, whatever ways to do that. I just haven't opened that yet. For your second question, have no idea.
Thank you very much. Just a question from the lipid perspective, actually. Yeah. Have you got any other comments on other elements of the lipid profile, HDL, LDL? How would you expect them to be affected by glucagon and by glucagon resistance, I guess?
Yeah. fatty liver patients do have their definite dyslipidemia profile in general at average. I think for an acute study like this, it's too quickly. You can't see the effects. I can't see any differences in HDL and LDL because it's just, it didn't get there yet. Maybe if I tested them in the evening also, I don't know. But at this point, no effect there. Yeah.
I think there's a lot of interesting questions here. Nikolai, for the next one.
Thank you very much. It's a major pleasure to hear your talk. So congratulations with all your efforts and results. So it's regarding the PNPLA3. Helen Hubbs from Dallas, I'm sure you know her. She's the person identified PNPLA3. Had actually a bit of literature about glucagon and PNPLA3 in that content. And I think we also see actually actions of glucagon on PNPLA3 expression. But what it's doing is still a huge question mark. Just what is PNPLA3 is doing? It's sitting on the lipid droplets. But I think it's very well in line with your data about with hepatic lipid, or at least triglycerides oxidation or beta oxidation. Yeah, exactly. Yeah. But my question is, if you could put some perspective in, for example, the dual agonists that are in different trials. Some are, being taken down, but is the effect we are seeing here, is that beneficial on glucose, on amino acids and lipids? And so do you see a future for dual agonists based on your data here? So you could also ask it in a different way. Can you overcome the resistance that you are seeing by adding a bit more glucagon in those individuals that have glucagon insensitivity or resistance?
That's a really good question, and I guess the honest answer is we don't know, but it should be tried, I guess. So I think with the dual agonists, it's really interesting if they are in fact able to reduce hepatic fat content. That would be a great effect. From what I know about them, they also perhaps increase resting energy expenditure a bit, perhaps also increase heart rate, what we do about patients with cardiovascular problems. And so I think the glucagon component of both dual and triagonists is going to be really complicated, and I think GIP and GLP-1 has a more bright future at the moment at least, but we'll see.
Okay, it was just a question about the development of the indices and the tests. I think that is really interesting. How do you can you give me a brief introduction? How do you plan to calculate insulin in the test where you give glucagon or give amino acids?
To calculate?
Yeah, to take into account that insulin may also influence your results.
Yes. Thank you for that question. So, insulin does increase as well, and to test the effect of insulin, there's actually a third arm in this study with type 1 patients with type 1 diabetes to take insulin out of this account. But we have seen in other studies from Steno Diabetes Center that patients with type 1 diabetes, when they get glucagon, as we heard about yesterday, there's also a decrease in plasma levels of amino acids.
A question also down that line. When I saw Malte's study, and perhaps also Sara's, the obese subjects had higher insulin, which, we know that. And you gave the somatostatin clamp, but they actually didn't suppress them fully. So, right? Yeah. Do you have any thoughts on that? And is that somatostatin resistance or what?
No. I think there's a lot of old publications. I'm sorry, is it okay? Stating that fatty liver patients do not clear insulin as fast as the rest of us. So it's expected. You can I'll never get a different result. It's not the somatostatin, it works. It's their own no clearance or reduced clearance that does it. And for me, it would have been nice to just have great curves, like right on top of each other, but then I would have the trouble arguing that this is not just insulin resistance we see, because they're also more insulin resistant. So what's glucagon resistance and what's insulin resistance? In this case, I had a higher insulin level, which would make the glucagon patient suppress more. So this is actually the best outcome I could have had. It's just really hard to tackle what's what in this world. Because I can have the best model ever, and it's still not eradicating the mistakes that we make. Does it make any sense? Yeah.
I can perhaps add to it that, so you're completely right that insulin concentrations weren't the same and they weren't suppressed fully. But what's really powerful about the method is that they are stable. Mm-hmm. So if we don't see any changes, the only thing that changes during the clamp is the glucagon concentrations. So the changes we observe must be induced by glucagon. It would be really weird that a stable insulin level would all of a sudden, at the same time, induce changes. So that's what really makes the method powerful to me. Yeah. Or convincing.
That was a really nice presentation from all of you. This is kind of more directed to Marie. With your urea data that you show here on the left. Well, you kind of mentioned throughout that presentation that glucagon increases, what is it called? PCS1, or what is this?
CPS1.
CPS1, yeah,
yes.
Exactly.
Yes.
And this produces carbamyl phosphate, right?
Yes.
And so this carbamyl phosphate is more or less analogous to pyruvate and that acetyl-CoA entry into the TCA cycle, sort of. It's analogous in that way. When you look at glucagon and this increase, the synergistic increase in urea production with amino acids, is it because of an enhancement in carbamyl phosphate synthesis? Or is it just somehow glucagon modulating the throughput of amino acid entry into the cycle?
It could be both. We honestly don't know these. So the effects happen very rapidly, right? So definitely it's some post-transcriptional modifications. It could be of amino acid transporters. It could be of CPS1 or also other urea cycle enzymes. So I know CPS1 is activated by a deacetylation. We don't know if this happens this rapidly. We don't know. Also, OTC, I can't remember the real name, another urea cycle enzyme, is also activated by a deacetylation. So that could also play a role.
Cool.
Yeah.
And would you expect then the glucagon treatment, where you see no increase in urea, to have an accumulation maybe of carbamyl phosphate?
You mean like without, when we give glucagon alone?
Yes, exactly.
That's a good question. But then, it depends where would the substrate come from.
Right, I think it's
right. I think we need to add some substrate, so the ammonia from somewhere.
Right. Cool.
Yeah.
Thank you.
So, if I could ask a question as well. So, obviously this session is about liver, and I love the liver, so I'm going to give you a liver question. I've heard you say, very interestingly, that steatosis, hepatic steatosis, gives us a model for glucagon resistance. But what about hepatic function? So when does that become impaired, so to speak? So if you've got inflammation, fibrosis, so I know it's a little bit outside of this particular box, but how would that affect your results? Will it become increasingly disrupted on all levels, or on particular levels of the pathways you've studied? So
at least with this biomarker of glucagon resistance, the glucagon-alanine index, that has been tested at the hospital, where they saw an increase in the glucagon-alanine index going from the a lean liver to hepatic steatosis, but it wasn't increased further when we went from steatosis to NASH. So it seems that it's just the fat in the liver and not the fibrosis that causes the glucagon resistance to amino acid catabolism.
I also guess in the acute setting, I would be really surprised if they had developed fibrosis in 2 weeks. So I think that indicates also that steatosis by itself is able to make the difference.
I think as a hepatologist wannabe, I don't think these patients that we include in these studies have a hepatological problem as such. Their livers work fine in many ways, doing what livers should do. But I think they do have a problem in the endocrinologist way, in the hormone and substrate metabolism way, that we as endocrinologists and wannabe endocrinologists and basic researchers should be interested in as a model and in itself, patients in their own rights for preventing all kinds of diseases in the future. Yeah. Does it?
Yeah, fantastic.
Yeah. You mentioned the potential of dual and triple agonists to modulate fatty liver disease. I was wondering if the level of liver fat actually determined the response, in other words, the level of insulin resistance, the resulting from the liver fat actually determines the response to some of these therapeutic agents, and not just for their liver defatting effects, potentially their effects on weight loss as well.
I'm sorry, was there a question?
More of a comment.
My question is, do you think that the level of glucagon resistance due to the level of liver fat determines the response to some of these dual and triple agonists containing glucagon for either their effects on liver fat, in other words, to reduce liver fat, or even their effects on weight loss?
Right.
I don't think so. I think much of the effect should come from the weight loss that they result in, and then I think it'll work. I don't know if anybody read anything else that should indicate otherwise, but, and also, they do respond, my patient. They do lower their triglyceride. So I think it's overcomable, but, my perspective. Don't you agree? Or?
That's a good answer.
We stop there.
So do we know anything about glucagon receptor expression in these patients in the liver?
There has been both human and animal studies indicating, but scarce. Only a few studies. I think maybe I had a few references up there. Yeah.
I know. I wonder about the results. I mean, it's pretty essential to know what the expression is like, and we don't know, right?
Yeah.
So we didn't see anything on the transcription level in the obese subjects. Yeah. In terms of glucagon receptor, the glucagon receptor.
Actually, I think I can comment on the previous comment on how much the liver fat matters for the weight loss of the triagonist, for example. And we did a lot of preclinical studies with the Novo Nordisk triagonist that we published in 2015, and we see that the higher the liver fat is, the better works the drug, right? So we never saw glucagon resistance, but when we take the triagonist into a mouse that lacks the glucagon receptor in the liver, the weight loss is dramatically lost, right? So it's not lost, so you lose the glucagon action on lipolysis and body weight, right? So the liver glucagon receptor contributes to the weight loss, and the liver fat is one of the targets that gets hidden by glucagon action in the liver, right?
Yeah.
And amino acids levels also decrease in response to these dual and triagonists. So they're not completely resistant, at least.
Just to comment on the glucagon receptor expression, I think it's, if you go to the literature, it's very variable what the findings you have on reductions or changes in glucagon receptor expression. For example, in your study you mentioned, Malte, there was no difference, but in other patients, for example, a study we have at Hvidovre, we see a clear reduction across NAFLD severity on glucagon receptor expression. So it might be context dependent. That's my point of view.
If I could, I just have to say something about it. So there's a lot we don't know, and the population is very diverse. And so even with the trials that we've had, phase 2, and now we're doing phase 3 trials, even with GLP-1 receptor agonists. So there's a benefit of the weight loss, but even in patients who don't achieve a significant weight loss, there's a lot of metabolic effects. And so I think this sort of shows us exactly why it's important to treat patients and to treat the underlying disease, and to factor in when we consider treatment, not only to target the fibrosis, but also the underlying disease, which is metabolic. So, but thank you so much. I think you've been in the